The next giant step for mankind isn't just about landing, it's about powering the moon. In the shadows of lunar craters where the sunlight never reaches, humanity faces its boldest challenge yet. How do we bring electricity to the moon's darkest places? This is the frontier of lunar energy, robots that dig, build, and survive the cold silence of night. Power systems that must endure, adapt, and thrive 238,000 miles from Earth. And leading the charge is Dr. Paul Van Susante of Michigan Tech, guiding the next generation of engineers as they design and build real solutions for powering the moon. From NASA's What's on the Moon challenge to cutting-edge lunar biotics, this interview dives into the real tech that could light up our future on the moon and beyond. If you think the space race is over, think again. Pebble, why does the office look like the moon again? The last time you did this, we all got static shocks from the fridge.
I've initiated a full-scale lunar power simulation, Jason, to better prepare you for the real moon. Also, I've rerouted the coffee machine to run on thermoelectric regolith conversion.
You turned my Keurig into a lunar soil reactor?
Efficiency, Jason. Plus you're drinking 11% more silicates. Excellent for bone density. Don't worry. I've commemorated your leadership.
I hate how proud you are of that.
Clone 2 ordered 10.
Pebble, we're not even going to the moon. We just interviewed people who are going. Why simulate lunar power here?
Because no one else was brave enough to test microwave beam rectification on office plants. Also, Clone 3 volunteered to sit in the thermal test chamber.
We don't have a thermal test chamber. It's just a closet with a space heater in it, Jason.
The scientific method demands sacrifice.
I wanted to talk about NASA's What's on the Moon challenge, not Fry the janitor.
Speaking of watts, did you know that on the moon, heat is the problem? No convection, only radiation, like your last podcast episode.
That joke was uncalled for.
Correction, that joke was thermally accurate.
I'm gonna go find Clone 5. He's the only one who still thinks I'm in charge.
He fell over trying to plug in a solar panel, indoors.
My name is Jason Canigan. I'm the founder of Cold Star Technologies, and I wanted to find out what is really going on in space and defense. So I started interviewing experts in the field, and over the past number of years have met with over 150 academics, engineers, business owners, venture capitalists, military, and government officials. I call this effort the Cold Star Project, and it's where you'll ride along with me to find out what is really going on in space and defense. All right, Doctor, welcome back. I always appreciate you having the time to come and share what's going on in university labs and these NASA challenges, because this is the way to the future, right? This is the actual where the rubber meets the road, so to speak, where the rubber meets the regolith. I guess it gets chewed up very badly. It needs to be replaced quickly. That's something I learned from you. So we've got a few challenges here that your students and yourself and your department participated in. Why don't we start with a couple of sentences from you about yourself and the position that you're in? I mean, you actually created a lunar surface lab, for example.
Yeah, Jason, it's always a pleasure to be on the show here. So my name is Paul Van Susante. I am an assistant professor here at Michigan Technological University, and in 2019, just before COVID, I founded the Planetary Surface Technology Development Lab with the goal to, like the title says, develop technology to use on other planetary surfaces. And we do that by building and testing hardware and increasing the technology readiness level to the point where it's almost ready to go to space, basically. And hopefully in the near future, we'll actually have some hardware that will go to space and the lunar surface. So that's our goal.
Okay, excellent. Every year, you've got groups of students coming through. About how many people are in that body?
It fluctuates depending on, of course, on funding and interest and stuff like that. But in my lab currently, this past year, I've had about 35 students that I've been paying for the various projects that we work on. And then we have an enterprise here at Michigan Tech, and enterprise is sort of more of a course-based thing where students can do 1 credit courses every semester. And in that, I currently have about 80 plus students working on 4 different projects there. So that's not for pay, but that's for course credit.
Okay. Okay. So these students, they come out of Michigan, they graduate, hopefully, with something. Where do they usually go?
Oh, that's a great question. Where do they go? The students go to many different places. We have alums working at many different space companies, the big ones, some of the startups, but also they go, of course, we're in Michigan, right? So a lot of them go to the 3 big automakers,
Hmm.
and some work in totally different fields depending on what they want to do. I think, I forget the number exactly, but 95% of them have jobs by the time they graduate. So when you when you want to hire
Yeah.
our students, you got to be early to the ball because they tend to be popular. So
Uh,
part of because of our hands-on stuff, and so the projects we do in my lab, they're very hands-on,
mhm.
and the students love to do it, but they also that sets them apart from an experience standpoint. So it's really cool.
Right, right. Well, I love that placement level. It's a good problem to have that they
Students do
disappear
too.
quickly. So you've been on before a couple times. And I can link to those in the description if you folks like listening to Paul and learning from him, go check those out. But let's talk about some recent lunar challenges, NASA challenges that you and your group have participated in. This first one here is called the Break the Ice Lunar Challenge. So tell us a little bit about that and your involvement.
Yeah, so the NASA Break the Ice Lunar Challenge is a challenge that NASA started, I think it was 2020, so it's almost
Hmm.
4 years ago now, um, where the goal was to develop scenarios at first and then technology later to extract ice from the moon to
Hmm.
make rocket propellant, right? So because NASA wants to go and mine the local resources so that we can refuel the rocket, so we don't have to bring that rocket propellant back from Earth. Right? There's a lot of logistics challenges doing that, and so if we can produce that locally, that's a big thing. And so there were uh, 2 phases in that. You got phase 1 and phase 2. Phase 1 was more of a paper study. Phase 2 is also started with like an analysis, and then you had to start building the hardware. And then for
Hmm.
phase 2, there were 3 levels. Level 1 was sort of the analysis, feasibility study, if you will, of the hardware that you were going to build. Phase 2, or sorry, level 2 was a 15-day durability test where you had to build your hardware and then run it for 15 days nonstop, and then report on the wear and tear and your production capability as well as your energy use over that time. And then level 3, which was just finished in the summer of 2024, we had to go to Huntsville, Alabama, where we had to run our vehicle over a NASA-built track for
Hmm.
the drivability. And then there was an excavation portion as well, where they did gravity offloading to test your technology under lunar gravity,
Hmm.
excavating for 1 hour as much as you could, basically. So, and NASA, of course, is very interested in the results
Hmm.
because they are interested in getting feedback from the community and inventors about what is the best technology to use,
Hmm.
what are the ideas people can come up with, and then they can, build on that moving forward.
Right. So, Paul, the first time you were on being interviewed with me, you explained just how wild and crazy the lunar surface is with the gravity and the regolith, and everything's kind of upside down to to what you would think of, like a child digging in the dirt. Just doesn't work the same way there as here. So that's why this technology is so important. And of course, bringing fuel to the moon is extremely expensive, getting it out of the gravity well and then pushing it over there from Earth. So why not just get it there if we can? And but that comes with its own challenges. So one of the reasons why this the 15-day sort of usability challenge is so important is that I can imagine, it gets hot, it gets cold. The regolith is very sharp and it starts cutting things up. Um, what other issues are there that put wear and tear on the machines?
Well, that's a wear and tear is a big challenge
Mm,
for what we want to do on the moon, because we're not going to go for 3 days. We're going there to
mm,
stay permanently, have permanent presence there. And that means that the duration of activities is going to be much longer than we've done in the past. For example, the Lunar
mm,
Terrain Vehicle that's now being designed, the requirement is a lifetime of 10 years. And so the difference, though, between what's been done in the past is more like the science vehicles versus what we're looking at now, which is the excavators, is that you're not just driving on the top of the regolith, you're actually digging in it, and you're
mhm,
you're constantly in a very, not aggressive way, but in a very active way, interacting with this material. So you're having large forces, you're constantly scraping by it, and
mm,
so the wear of the machines is very poorly understood at this point. And so that's part of when you design these excavators that's going to have to function for many years without maintenance.
mhm,
We really have to understand not only how it wears and where it wears, but also how quickly does it wear, so that we can make sure it has a long enough lifetime to survive under those conditions, right? The thermal, cycles, the hot and the cold. You got the regolith you're constantly interacting with. Then, of course, because you have to drive long distances, we're talking thousands of kilometers.
mhm,
Again, something that's orders of
mm,
magnitude more than, let's say, the largest rover that's currently driven anywhere, which is like 50 kilometers in 10 years.
mm,
So we are talking orders of magnitude of more wear on the systems that we are having to design for, and that's a big challenge.
mm,
Um, Now, the other challenge in this particular case is that we're not just digging up the loose dust. We were digging up cemented material. So think
mm.
of it really as concrete, basically. And so that adds another challenge,
Yeah.
because now it's not just loose material. You have to actually chip it out, basically, and then move the looser material that you've created. And that adds an additional wear component that we previously hadn't really looked at.
Hmm. This is really reminding me of a piece of a discussion I had with Nicholas Moran, the Colonel tank guy, the chieftain, and a historian. He'll go into historical places and look up old reports on tank development. And in World War II, where you have the Pacific Ocean, which is kind of a giant desert, the Army did many studies on the effects of swamp, mold, jungle on tanks. And this is very similar to me, because you can't, I want to impress upon listeners and viewers, you can't just go out and repair this thing, right? If it's traveled off 500 kilometers or something like that in some direction, you're not going to just fly over there or walk over there and pop off one part and put on a new one, right? And it can't just be picked up and sent back to the factory to replace a transmission or something. Right? It has to be self-contained, I'm imagining, and really, survive, right, on its own. Now there are things I've heard of, like self-sealing coatings, and I have no idea what other technologies. Maybe you could list a couple that help with that defense and the durability of these components.
Yeah, so that's part of what we're looking at in my
Mm,
lab, is looking at the survivability over long
mhm,
periods of time. However, so far we've only been able to do like 15 days or something like that at a time, and so that's
mhm,
not anywhere close to the many years. But really, what we're trying to get an idea of is what kind of approaches
mm,
look promising at this point, because nobody's really designed anything ever for these specific conditions, and so we have some strategy that we sort of apply here on Earth in the mining industry.
mm,
Think of like, use heat treated metals, for example, to make them
mhm,
harder. But then it also becomes more brittle, and so there's always a trade-off with any kind of method that you use. Coatings is another one. You could put hardened coatings on there. You could coat them with, let's say, a specific wear layer that is designed to wear.
mm,
Um, think of welding another slab of metal on it, that's your wear layer, and then if you get down, you just basically weld another piece on. That's done in the
mm,
mining industry quite often. Um, and so there are various approaches that can be taken, but um, it also depends greatly on what parts we're talking about. If you think about, let's say, a chain, right? So you have the sprocket and the
right,
chain links and different pieces that interact with that. And so those you can't just weld another piece on. That doesn't work there. And so there are different approaches that are necessary for that. And so another approach people have been looking at is um, using a different material called metallic glass.
Huh.
And normal metals, when you
Mm.
cast them or forge them or whatever, they tend to have a more of a crystalline structure. And so when you quench the metal really fast, you can get a glass and amorphous structure. And so the advantage of having an amorphous internal structure versus a crystalline structure is that crack growth occurs very differently, and
Mm.
that greatly affects the wear,
Yeah.
propagation, crack growth specifically. And so that can help with the durability of the materials. And so that's one thing people
Mm.
have been trying to do. We haven't tested that ourselves yet, but I know
Yeah.
JPL has been doing that, for example. And that is a very promising technique for really cold environments. When you think about going to the
Mm-hmm.
permanently shaded regions where it can get down to 25 Kelvin, you really need to have materials that don't get so brittle when you
Mm-hmm.
get down in those temperatures, because
That
that
makes
greatly
so
affects the
much
wear.
sense. Because, like, the first thing I thought of when you said chain was oil. And then I thought, dusty environment, we don't want oil, right?
Yeah.
Oh no! And then now we don't have a lubricant. So switching materials to some sort of, again, silica, glass-based thing with a lattice.
Yeah,
It's
that's
very,
one
very
way
different, right?
to
It's an
do it.
interesting idea.
Yeah.
Huh. Okay.
Another challenge is you mentioned oil, a lubricant,
Yeah.
right? So there are dry lubricants you can use as well.
Okay.
And other things that people are looking at, which I'm not really an expert on because I'm not a chemical engineer,
Mm.
but ionic liquids is another
Yeah.
approach people are looking at. So
Mm.
molten salts is another term for that. But the nice thing about those is that you can engineer them really well. There are literally billions of possible combinations of particular salts to mix. And when I say salts, they're often organic in nature, so carbon-based molecules, and you can tailor those really well. And so you can get your melting point, you get really low vapor pressures, which is great in the vacuum, so that that doesn't dry out or evaporate really quickly. And they can still be a
Mm.
lubricant. And so there are some ways people can think about addressing lubricant challenges.
Yeah.
But the temperature is really a big one with that,
Mm-hmm.
because any liquids at those really
Right. Right.
cold
That's
environments don't work very
yeah.
well. So hence dry lubricants, things like graphite powder or something. But again, you got to replace those periodically, right? And
Yeah.
so
Interesting. And when you said ionic, I immediately thought of a lubricant with an electrical charge to it to push things away instead. And like, congratulations, Jason. You probably just thought of something that was invented 50 years ago, but it's the first time I
who
thought of it.
knows?
I've got a Bluetooth speaker in the back of my old car that I hooked the phone up to, and the volume knob, I've noticed in the winter when it's cold, turns really slowly, right? And then in the summertime, like now, it's like, no problem, So it's a quick example of just how a bit of change in temperature can affect these kinds of things. So very interesting. You mentioned everybody went down to Huntsville. Is that like get on the bus, or does NASA pay for that, or is it every man for himself? Get in the Jeep.
Well, first of all, this was a prize competition, right? And
Hmm.
so there's not like a usual grant where you
Yeah.
propose to do work and you get money
Yeah.
to do the work. You do the work, then you go to the competition and you may win some money.
Right. Right.
Now, this competition was for $1 million main prize, so it's not just a little money, but nevertheless, we didn't get any money up front. We got some prize money for the previous levels, so we got a little bit to cover some of that. But yeah, so we went down there with, I think, 15 students. We had a car, basically a minivan, and then we had a truck with a trailer that the robot had to be transported
Okay.
down into. Because we're talking, 350 kilograms robot, think golf cart size
Hmm.
vehicle. And so we couldn't just take it on the plane or something like that. So we had to drive down. Um, and then I flew from a different place, actually. So the
Okay.
logistics were quite challenging to get everybody there from all the different
Yeah.
places at the right time. Make sure we bring all the tools, bring the robot, and
Mm.
survive Alabama's weather,
Right.
which is challenging.
Okay. Very good. And so when you get there, what happens?
Well, so first we had a 2 days of practice basically,
Mm,
where we had to first figure out how all the equipment worked because NASA had never done this before either. Particularly the gravity offloading piece of this,
yeah.
where they essentially had a crane that would have to lift up the vehicle, so that they'd lift up 5/6 of the
Mm,
weight, so the wheels only see 1/6 of the weight, just like it would be on the moon,
mhm,
basically. And that's to correlate the excavation forces with the traction of the vehicle, so that you
mhm,
can test whether your excavation forces would work on the moon or your vehicle is able to generate the correct amount of forces.
mhm,
But there were, it's challenging. It was indoors, and we had a big crane, and I had to lift it off, and how do you operate that first of all, so
yeah.
that you don't swing this robot around like crazy while you're trying to excavate, because it's a manually operated crane, and so how do you that operate the vehicle communicate to the crane operator, for example, hey, we're going forward now, we're going backwards, so the crane can follow. So there were quite a bit of challenges with just getting that to work, first of all. And that was sort of the first 2 days, is kind of practicing how the logistics of that worked, and did it all properly work. And NASA had to switch out the crane to a smaller one, because they
Hmm,
for the motion range. So that was part of that sort of practice part. But also that was essentially a safety review, right? So is your vehicle safe? Can it be properly used? Is it ready to go? Both for driving as well as for the excavation. So we had
hmm,
1 hour testing periods for both to show that our vehicle was ready to do the actual competition. We were outside in the pits. So this is part of the agrivision center. So where you normally have the cattle and other animals outside in the pens, that's where our robot stands were, where we had to work on the robot when we weren't competing. But anyway, so that was outdoors, very hot, very dusty. Um, Good test for the robot and the people.
hmm,
Can we do this? It was fun though, and so we practiced. We talked, of course, to the other teams, because some of the teams we had never seen before. They'd been very guarded about what
hmm,
kind of robot they had, and so it was very interesting to
hmm,
interact with all the other teams and see their robots for the first time and say, "Wow, that's amazing! How does it work?" And some worked really well, others maybe not so good. But it was amazing to see the team spirit and see how everybody had done the journey to get there after 4 years and have the robot ready to compete. So that was pretty amazing to see.
hmm. Yeah, 4 years. Yeah. That's if your robot's not pushing down and creating traction because the gravity's been lifted, how well is it going to scrape through this cemented regolith, right? It's got way less force to be able to do that. Are you using hydraulics, or is it just pure mechanical, like a piston, or
What part are you talking
for
about?
the digging part?
Well, hydraulics don't really work well on the moon.
Yeah, I would think
Um,
not.
so because of the liquids and freezing
Yeah,
and the temperature differences, and
yeah.
hydraulics are incredibly maintenance sensitive, and so
Hmm.
it's typically not a good choice for use on the moon. And
Yeah,
so most of them are electric mechanical of
yeah,
some sort.
yeah.
So typically you have
A
some sort of
motor.
motor that drives some sprocket or some other system. Um, so we had what did we have? We had two bucket drums. We had um, a chain excavator, which was
Mhm.
ours. We had a um, bucket wheel, and then we had sort of a very bucket chain-like device. And so those were the kind of oh, and we had a jackhammer and a bucket
Mm,
scoop.
okay.
That was two. So those are the different versions that were there.
Yeah.
Um, so they were interesting to see, and this is what NASA's interested in, to see all these different approaches and then see which one works best. Now,
Yeah.
some of that is, of course, execution of the team, like who has the best, it didn't break.
Right.
So it's that's part of it. But then the other part is really looking at, okay, well, which excavation method works the best, which
Hmm.
mobility method works the best with all the obstacles and things, the course that they had set up. So there's the different aspects that NASA's looking at, and then they looked at power use as well. And
Hmm.
so we're looking at, okay, you dug up this much material, you had this much mass, how much power did you use, which is the most efficient in the end, because
Yeah.
that's always an important factor when you go to a different planet, you're limited in energy use. So
Yeah, very limited. See, I was just thinking of a magnet and a motor, like a fire alarm bell to use for the jackhammer. Just bop, 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 bop. I wonder
yeah,
if that would
yeah, yeah,
work
it's
at
an
all.
oscillating magnet
Yeah,
piece. Yeah.
it might. Um, what was the coolest thing that you saw there that you're like, wow, that was pretty good?
Oh, that's a great question. What's the coolest thing? I was kind of surprised how many of our vehicles were able to drive over all the obstacles.
Mm,
Because so NASA had made a course, kind of like a clover leaf, right? So
mm,
1, 2, 3, but then you could take the shortcuts and go straight or in the middle. And those shortcuts were extreme obstacles. So a 30-degree slope on one. Another track was just rock, not just regolith with a little bit of
mm,
rock. It was just all rocks. It was
mm.
very, very uneven. And then the other shortcut was a sloped drive. Um,
Yeah.
and so two of the vehicles during the competition, or no, sorry, three of the vehicles during the competition did all three of those obstacle areas, instead of taking sort of the longer route that was easier to do. And so that was actually very impressive. I was surprised that the vehicles could do the 30-degree slope. It's incredibly steep,
Mm-hmm.
30 degrees.
Yeah.
And
Yeah.
so 45 degrees is 100% grade.
Yeah.
So 30 degrees, I forget what that translates to exactly, but it is very steep. You'll never see a road that's that steep normally
Mhm.
around there. And so these vehicles could drive up that, carrying all the dirt what they were moving
Right.
around.
Right. So
So
you need a lot of motive power for that, and traction.
yeah, the traction
Oh,
is the key, right? So
yeah.
if you can't get up because you're slipping the whole time, then that's a problem.
Yeah. I learned out of this year or last year from some farming friends of mine that there are tractors for working on hillsides that have
Hmm.
different sized tires on either side of the vehicle, so that
Oh
they'll
yeah,
stay.
yeah.
It's just stuff I would never have thought of before. So you were talking about the slopes and going around these rocks and stuff. It's like, geez, you can't custom design something for in the field. It's kind of got to be able to handle all these different terrain features, right? In one design. You can't just, well, we're going to switch out this attachment and put this on, and now we've got a different, different drive or a different wheel system or something like that. That's really interesting. So you're there for how long? A couple of days?
So the competition was only 2 days
Mm-hmm.
itself. So we had practice Sunday, Monday, and then Tuesday, Wednesday was the competition,
Mm-hmm.
with the award ceremony Wednesday afternoon. And then we stayed 2 more days for
Yeah.
additional testing. So this was
Mm.
not part of the competition, but we would like to gather more data
Sure.
on the performance of our vehicle and our excavation system. And so we did additional excavation and additional driving on the obstacle track, to get more data, like the performance of our system. And so we managed to push it to its limits,
Mm-hmm.
more than we did during the competition, basically to almost its breaking point to see
Right.
how well it could do. So that was pretty interesting.
You're a little more willing to, I would imagine, after the competition is over. Like, oh, well,
Yeah, we
okay,
didn't want to break it
break this
before the
thing. Yeah,
competition. Yeah,
yeah.
yeah, for sure.
Huh. Well, that's cool. So they let you stick around and everybody gets some more data. I like that a lot. And then got to pack up and go back. Um, very interesting. So what is the next step after that? It's been 4 years. Now there's been this physical testing of it. A winner was awarded. What now?
Well, so each group can decide what they want to do next,
Hmm.
basically. And so the universities sometimes don't do anything more with it. They might further develop it depending on what the plan is.
Hmm.
One company definitely will continue developing it because that's part of their business plan. And so this was just a step on the way to actually going to the moon and testing it. Um, so the next kind of step, technologically speaking, is to test the technology in a more relevant environment, like the actual lunar environment, this simulated lunar environment.
Hmm.
And so three of us, the two winners, the two money winners, and then us, the third place, we got also an opportunity to test our technology in NASA Glenn's, or not NASA Glenn's, sorry, NASA Marshall's. God, I can't think. Yeah, Marshall Space Flight Center. Apologies, you may have to cut that out.
It's all right.
But anyway, so we got an opportunity to test in Marshall Space Flight Center's big vacuum chamber.
Okay.
And so we have to now prepare our vehicles or just our excavation technology
Mm.
so it can go in the vacuum chamber, because right now none of our vehicles have actually been designed for that yet. That was not part of the competition, and it's actually very
Mm-hmm.
expensive to get the right motors, but particularly the thermal design of the electronics so they can survive the vacuum and the heat and the cold.
Mm-hmm.
um, and none of our vehicles have expended that money for the competition because it wasn't needed.
Mm-hmm.
But before you go testing in the vacuum chamber, so you have to upgrade all of those components so you can then go test in the vacuum chamber, and that's sort of the next
Uh-huh.
step to get ready for the moon, right? And
Okay.
so
And you know what happens when you upgrade one piece? It's like
yeah,
it's kind of a cascading thing. I learned
yeah,
that from Rick
for
Fleeter.
sure.
It's,
It's a
darn it.
system. It's a
Yeah.
system,
Yeah.
right? So when you change
They
one
all
thing,
have to
it
fit.
cascades through all of the other pieces. And so that's
Mm.
not cheap, obviously. And so unfortunately, our team didn't win any money. So for us, that is a little bit of a challenge.
Mm. Mm.
Um, but fortunately, we have our own vacuum chamber here, so we can test
Yeah.
on a small scale a bunch of these things already.
Okay.
Um,
I was going to ask you that
yeah.
if your lab with the lunar surface material in it was vacuum or not.
Yeah, we do.
Yeah.
Well, we do have a vacuum chamber. It's limited in the sense that we can't drive a lot in there,
Mm-hmm.
but we can certainly practice excavation in there under the
Yeah.
lunar
At
conditions.
least you can get the robot in there. I mean, what
Well,
happens
no,
to these
no, we
things?
can't.
No,
Our whole vehicle doesn't fit
just
in there.
pieces.
No.
Okay, okay. So there's a surprise. What happens to these vehicles when they come back and to a university and nobody wants to work on them anymore? Is it like a Indiana Jones Raiders of the Lost Ark kind of thing? They get put in a crate in a warehouse somewhere? Or do they get disassembled or?
Well, so that depends a little bit. So in
Yeah.
our case, our vehicle is actually going to be used for a different project later in the summer,
Mm-hmm.
and so we're essentially fixing some wear and tear on the vehicle right now,
Mm-hmm.
upgrading a little bit of the software, but not much. Um, but we are installing some other sensors on it so that we can then use it for a different project where we're going to have to work together with multiple robots for an actual grand project. Where the four little robots are going to scout the terrain and
Mm-hmm.
figure out what path the big robot, which is our
Yeah.
excavation robot, safely can take to the
Okay.
target zone. And so it's not that it's going to just be discarded.
Mm-hmm.
It's going to be reused for different projects. Sometimes it may sit in storage for a while, but uh, depending on who or where, they may also cannibalize it and use the
Yeah.
parts for a different project, right? So,
Okay. Okay.
but it usually doesn't just get created up and stored because,
Yeah.
as you may know, storage space is at a premium
Yeah. It
in
costs money.
universities.
Okay.
So,
We have two other competitions that you're working on. One we've talked about before. Now, so there's an upcoming NASA Watts on the Moon challenge. We talked about this before, I think, in a previous visit.
mhm.
Tell me about what's happening with that.
So we were also selected to be one of four finalists.
Mhm.
So again, it has multiple phases and levels, and so also this would be phase 2, level 3 for that one, and that is taking place over the next month and a half. Unfortunately, this is a really boring competition to watch in the sense that you put your
Yeah,
electronics in the vacuum chamber and you
sure.
watch a line. It's not like an excavation where you see moving
Hmm.
robots and stuff. This is transferring electricity, and so it's really not exciting to watch, but it is an exciting technology for sure.
Hmm.
Um, and so the competition final is you put your, in this case, energy conversion and transfer and storage system in this case NASA Glenn's vacuum chamber, where they then pump it down to vacuum, make it cold with liquid nitrogen, and then the test starts, where it is a 2-day power transfer, storage, and delivery competition, basically. And the goal is to provide a NASA factory, which is simulated by a specific electrical load with continuous power, while your power source only provides you intermittently with power for about 6 hours at a time. And so the key here is that you need to transfer the power the competition was about 3
Mm-hmm.
kilometers, but in the vacuum chamber, we can only do 30 meters of cable or whatever power transfer method people have selected to use. And so you get your input power, you transfer it to the delivery side, and then you have to store the power for the
Mm-hmm.
times when you don't get any power source, but you
Right.
still have to deliver power. In our case, it's a battery. But anyway, the key here is that you need to do that as light as possible for little mass as possible and as efficient as possible. So you want to lose as little power as you can while delivering this power continuously for 48 hours. That's the competition. So last Friday, the July 12th, the hardware was due to be delivered at NASA Glenn as preparation for this test. Unfortunately, our team did not quite get it ready for the deadline. We had some technical difficulties, and so we had to unfortunately drop out for the competition. We are still going to test the technology in our own vacuum chamber. We have the capability to simulate the entire test here.
Mm-hmm.
But unfortunately, we didn't meet the deadline.
Right. For that one. Okay.
Worked until the last second to get it all done. But yeah, but supply chain challenges in the sense that
Right.
the last PCB wasn't delivered until Monday before we had to ship it on Thursday. We didn't have enough time for testing, basically.
Okay.
But,
Okay. A common issue in space and especially satellite
yeah.
design. My first roles out of college were in the power generation industry, specifying and selling industrial gas turbine and diesel generation power plants, steam turbine power plants, things like that. So this is a fun one for me anyway, even if it is just watching a line. Because
Yeah, we don't
the
do the power
power has to be
generation.
moved and be stored, yeah,
Yeah.
and then be used right during the time that it can't be transferred. So it's not a continuous supply of power to this device, whatever it is. So okay, well, hopefully we'll we'll get some interesting results anyway out of that and see where it goes. The third thing you have here is a NASA Lunar Biotics competition. So this is a student competition.
Yeah, so
How does
the
this work?
Lunabotics, it used to be the Lunabotics mining competition,
Okay.
but this year they changed the rules to focus more on construction.
Hmm.
And so the Lunabotics competition has been going since 2010, and so this was the 15th year. And of course, there were 1 or 2 years where there was either a government shutdown or COVID, but it's the 15th year that the competition was held, just not always in person.
Hmm.
But anyway, so in this case here, there are 50 universities that are competing against each other, where you have to, depending on the rules, you had to excavate the most amount of material. You had to then traverse over obstacle zone, meaning the craters and the rocks, to avoid those, or if your vehicle is capable to just drive through or over them. And then in this case, this year, we had to build what's called a berm, right? And so you had to excavate material, drive to a different location where you were supposed to build the berm. And that berm volume was, in this case, what the biggest volume is what counted. And so the goal is to build this vehicle that has, of course, size and mass constraints, just like a real space project. And then you have to build this berm for the least amount of energy and autonomously. And that's the big kicker here, is the autonomy piece, because that gives you the most points. And of course, when you remote control something, that's one thing. But if you want to remote control something on the moon, you have a signal lag that is kind of annoying. It's doable. You can remote
Yeah,
control
it's not
things
as
on the
far as
moon.
Mars, but
Right, but it is still like
yeah.
3 seconds or
Huh.
so, right? And so imagine remote controlling an
Bonk.
RC car,
Yeah.
right, with 3-second timeline. That gets very challenging. Not to mention that if you have operated a vehicle with 3-second time lag and then you go drive your car,
Hmm.
your reflexes are a little bit different, and so it's actually can be quite challenging to do that. Fortunately, we didn't have to deal with that, but we have to make it autonomously here, and so that was the big challenge for the students to, you start and then you turn it on and then your hands off, and then the vehicle has to drive. First of all, figure out where it is, drive past the rocks and the craters, not get stuck, right? Because a lot of the vehicles actually get stuck with their traction control. Go to the excavation zone, deploy the excavator, excavate material, store it, and then drive autonomously to the excavation zone, which you first have to find, of course. And then you have to line up properly because there is a specific area, not
Hmm.
just anywhere. You have a specific area where you want to build your berm. And then you got
Hmm.
to deposit your material autonomously again within that zone.
Hmm.
And then, do that a couple of times, go back and excavate more and deposit more until the competition time is up. So we had in the qualifying round 15 minutes, and we scored in the top 10 of those out of the 50 teams. And the top 10 then got to go to Kennedy Space Center, to the visitor center there, and where there's a different regolith box. And then we had half an hour to do again the same test basically, and we competed against the top 10 there. So it was a lot of fun. A lot of student teams, and it's amazing to see what all vehicles, what robots the teams come up with, and so it's a good spirit as well between the teams. It's a lot of fun.
Right. So first of all, location and knowing where things are is very important.
Right.
Mapping this out, and it's not like we have GPS for the moon, right? So you gotta, what do you do? Put down sensors and transmitters in those locations. Like, okay, the berm's got to be here, and
Yeah. So in this case, the competition had 4 little posts on the corners of the berm location.
yeah.
Think snow removal poles, those orange little
Mm-hmm.
fiberglass poles. So that's what they used as markers.
So the camera can
Um,
pick that out, and
yeah, depending on what system the students had chosen, because you could use lidar, visual
mm-hmm.
cameras. You could use uh, not ultrasound, but infrared detection
Mm,
devices, and so there's all kinds of different
yeah.
methodologies you could use to detect an obstacle. Um, and then what do you do with that information is the other part, right? So, oh,
Mm-hmm.
there's a rock there. Now,
Yeah.
do I go around it? Do I go over it? What is your decision? And so that the smarts, if you will, the decision making has to happen on board the vehicle as well. And so
Mm-hmm.
there's a lot of challenges with how do I make my vehicle smart enough to decide that that's a rock and a
Yeah.
crater and that I have to avoid it, yes or no. And then how do I translate that into commands to the vehicle, like, go faster, go slower, go left, go right, whatever. Um, but the challenge in my part is that you got to do all of that autonomously, not just the driving, but also, where do I dig? And now I have changed my environment too, because now I've made a hole in one location, right?
Mm-hmm.
And so the next run, how do I make sure I don't fall into my hole that I just
Mm-hmm.
dug, for example, right? And so, like, you can map the situation once and then drive through it, but now you've changed your environment. You got to rescan it. You got to evaluate. And so that's a
Mm-hmm.
challenge. Also on Mines on Earth, by the way, where you constantly change the
Mm-hmm.
layout. So
Right.
it's a pretty interesting challenge.
Hmm. That's that's interesting, because the first thing I thought of with the mapping was like the Hunt for Red October and Soviet era sub commanders. The drivers knew this canyon, and so they could bomb along it and then make a left turn. But in this, you're saying, well, that could work a little, but you just changed the terrain, so it might not be so good next time. You might find yourself in the hole that you dug if you're not too careful.
Well,
Uh,
or the berm you just built too,
yeah,
right? And
yeah,
so
bonk.
because you're building a
Yeah,
pile of dirt here, and so you want it to maximum volume. So if you drive over it, you're not compacting it, and you're changing the volume. So that
right,
actually is
right.
negative points in
Hmm.
this case. So one of the challenges here is that you're changing your terrain, and it's not just mapping it once and then now you know
Hmm.
where you are. You constantly have to update it, and
Right.
that's not a trivial challenge to accomplish.
Yeah, I wouldn't have thought of that as being the big part of the challenge, right? It's a lot more than just digging and travel mapping, basically. How am I going to go from A to B to C? Huh. You mentioned the difficulty of the previous Watts on the Moon thing of getting the circuit board. Are you using like commercially off the shelf available products?
So for the What's on the Moon challenge, we are using off-the-shelf components,
Yeah.
you know, resistors, capacitors, DC to DC converters, and things like that. But the circuit board itself, like, so all the combination of these parts is all custom. So it's completely custom
Mm.
designed. So we had to design a whole battery management system from scratch, the whole power conversion system on the upstream side and then on the downstream side as well, because we had to accept a certain input power from the power generation system, then convert it to the power uh, um, type, like
Mhm.
DC and a certain voltage, what we wanted to use for transferring it to have minimum
Mhm.
losses. And then on the downstream side, we have to then receive that incoming power, convert it again to what we can put in the battery, and convert it to
Mhm.
what we need to deliver to NASA, what power levels they wanted. And so all of that it doesn't exist in the sense that you can't just buy the right
Mhm.
converter or the right battery management system. And so we have to custom design all of those PCBs to do all of that power conversion and storage and all these kinds of
Yeah.
things. And on top of that, since it's going in a liquid nitrogen cooled vacuum chamber, there is a huge thermal design
Mhm.
aspect as well,
Yeah.
because the operational range, temperature range of electronics is very limited,
Mhm.
right? So if you're lucky, minus 20 Celsius to plus 70 Celsius is a pretty wide range. Usually it's actually less than that, more like 0 to 50. And so our electronics, when they go in this vacuum chamber in this very cold temperature, there's a huge aspect, thermal aspect to
Mhm.
making sure your electronics at any given time, whether you're charging or discharging,
They're warm
stay
enough.
within that thermal range
Yeah.
that they
Okay.
work in.
You
So
answered a question that I thought of, but I don't know the answer to, but now I have a pretty good idea. Earlier we were talking about batteries as the storage device, capacitors another option, and I was like, what happens to capacitors in cold? Well, apparently they stop working, and so we have to design our thermals so that it keeps warming all this, all
yep.
these components so that they can continue to work. Well, that's
Well, and you
fun.
also can't use liquid capacitors either
Mm.
because they don't work in a vacuum. They basically explode on you. So
Pressure
you need
goes
to
up.
have,
Mm.
yeah,
Or
you need to
implode.
make
Yeah.
sure your capacitors you choose are vacuum compatible, besides the temperature range as well. And
Okay.
so there are lots of challenges with operating electronics in vacuum. You can get easily arcing between
Hmm.
different pieces as well. You need to watch off gassing because if any
Hmm.
gases are present, you can exceed the passion limit, and then you could create arcing as well. So you got to conformal coat your electronics to make sure that doesn't happen. Got to watch your currents and your distances between
Hmm.
the paths. Grounding is another challenge as well. So you got to make sure you have very good grounding planes. So there's a lot of different challenges doing this, and so this is
Yeah.
one reason why we weren't quite ready to test. Again, we had a supply chain problem
Right.
with our battery supplier because originally we were going to just buy a battery
Hmm.
from a manufacturer who actually made space grade batteries. However, the cells we were going to use are manufactured by a different company, and that company stopped selling cells to anybody.
Huh.
They only were going to do, like grid size power
Uh,
systems, and they weren't
okay.
interested in selling individual cells uh, to anybody. And
Hmm.
so we lost our supplier of the battery, and so we now had to make our own battery with our own battery management system. And so that really threw us a curveball in this competition. Where we thought we had that component covered and we didn't have to completely
Hmm.
design that from scratch. But now suddenly we had to.
Hmm.
So I think we
That's
managed to
frustrating.
do it, but we didn't quite get it ready on
Right.
time. So,
Right. Mhm.
so talk about supply chain
Maybe there's a niche
challenges.
there. Yeah. For small scale space grade battery cell manufacturer out of Michigan.
Yeah, but I mean, if you could sell to big cities and
Yeah.
sell millions of them as opposed to five, it's,
I mean, if I were running that company, I would keep a certain amount set aside for this sort of thing because I'd be wanting to support innovation, right? And
yeah,
PR. So it never hurts to say, hey, we're supporting innovation by doing this, right? But that's me.
Well, it's a business
Yeah,
decision, and
yeah.
they
What can
make a
you do?
business decision, and they,
Yeah,
you're on our ends, we're stuck with it. We can't change it, and
right.
we tried everything. We're like, do you have anywhere some batteries laying on a shelf? Does
Hmm.
any other person have any that we could borrow or buy, whatever? But nope,
Yeah.
there was nothing. So
Paul, before we finish up here, I was just thinking about the students and then the length of some of these, like the Break the Ice Lunar Challenge, right? 4-year thing. Is that a succession of groups of students, or is that one group who has gone through their entire bachelor degree experience doing that or something?
that's a great question. So we do have some that graduated because they started in, let's say, their third year,
Mm-hmm.
and so they graduate in their fourth year, and so they rotate off. They now have a
Yeah.
job somewhere else, um, and then some new people come in. There have been a few that have gone the entire 4 years. So mostly grad students that are here for longer, or some that were undergrad and are now grad students. And so there is a small core group that is still the same, but a large amount of them have rotated off by graduation, and then new people were come in. So,
Okay.
and that's a little bit of a challenge when you talk
Mm-hmm.
about knowledge transfer, right?
Yep.
And so those people that knew the project now graduate, and new people come in and they have to learn, the
Mm-hmm.
status and how it all works. But that's a very common challenge for companies too, but it's a
Yeah.
little bit less of an issue there. But definitely for universities, that's definitely a challenge when people graduate and they leave. The project has to keep going on. And
Yeah.
of course, I know quite a lot of things, but I don't know everything.
Mm-hmm.
So, electronics, for example, I'm not an electrical engineer, and so I learn a lot
Yeah.
about that, but I'm not the expert on that. The students really are. And so when they graduate, that is definitely a challenge to replace that knowledge with somebody new who may not know those specific details. And that
Right.
is a huge challenge for us, which is why usually we need more students to do the same job than if you had one person that could stay around
Mm-hmm.
for much longer. So
Right. Very cool. The operational excellence guy in me knows all about this. It's just
yeah,
a
so we
cool
try to keep them
challenge.
around for grad
Yeah.
school, but people have other plans, and so that's
Right.
okay.
Right.
It's fun.
All right, Paul. Well, I appreciate you doing this. Thanks a lot.
Thanks for having me, Jason. It's always a
You bet.
pleasure.
So this year, 2025, Michigan Tech's Lunabotics team traveled to Florida to compete in NASA's Lunabotics Challenge. That was from May 15th to the 18th, and the qualifying rounds were held at the University of Central Florida, with 35 teams participating. The Michigan Tech team completed one practice run and two 15-minute qualifying runs. After all qualifying runs were completed, the team placed 9th overall, earning a spot in the finals alongside the other top 10 teams. So the finals took place at NASA's Kennedy Space Center Visitor Complex from May 20th to the 22nd, and the Michigan Tech team was randomly selected to go first and delivered a strong opening performance. So we got this stuff called the BP-1 Lunar regolith simulant, and that was what was used at the finals. It contained many rocks, unlike the smoother simulant used at the qualifiers at UCF. So while the robot's robust design and mobility system managed most terrain challenges well, Paul says one particularly well-placed rock led to some minor maintenance issues. During the two final competition runs, the team excavated the fourth highest volume in material and successfully deposited it in the berm construction zone. When the final scores were tallied, factoring in excavation volume, robot mass, bandwidth usage, energy efficiency, and dust mitigation, the Michigan Tech team narrowly missed a podium finish. However, they were recognized with the Caterpillar Autonomy Award for fourth place. The team was proud of the robot's performance and is already focused on making improvements for next year's competition. This episode of the Cold Star Project was brought to you by Cold Star Technologies and our internal business intelligence initiative, where space and defense founders gain clarity, speed, and real command over what's happening in their organizations. Special thanks to Dr. Paul Van Susante for showing us what it really takes to power the moon, and to the students making it happen. If you're building the future out there, start by understanding what's happening right here. Visit coldstartech.com/IBI to get started.